So all right. So again, just as a little bit of a refresher from what we did yesterday, right? Yesterday, we got into a new unit, right? We just finished up looking at the derivative in kind of like introductions, in an introductory sense, I guess, an introductory sense. And now we're moving on to applications of the derivative in this chapter, this section, all right, this unit. So the first thing that we kind of looked at is how, we can, well, I guess extrema, and we'll kind of we'll explore that relationship a little bit more later. But we came up with some different kinds of extrema. Again, extrema is just the plural of extremum, and it talks about extreme values, right? Maximums and minimums, highest and lowest points, or relatively highest points and relatively lowest points, right? We talked about absolute extrema, okay? Also sometimes known as global extrema. Okay, it's the highest point of a function, the lowest point of a function. And of course, if you saw from the homework, right, we saw that there can be more than one location for the highest point. For example, sine, the graph of sine, right, has an infinite number of absolute maximums, and they all occur when, when the y value is 1, right, because the highest y value for sine is 1, but it hits that an infinite number of times. Likewise, sine of x also has an infinite number of absolute minimums. They're all the value whenever the sign is equal to -1, right? So you can have more than one location for the absolute maximum, but you will only have a single highest value, right? You can't say that, the function's highest value is 3 and 5, well, because 5 is the higher one there, so you just say the 5, right? So anyway, you'll only have one maximum value, but you can have many locations for where that maximum value occurs in your function, okay? We talked also, right, about where places that the maximum value can exist or does not exist, right? And then we went to this very important extreme value theorem, right? It's named, so it's probably important, and you need to be able to use it and apply it in situations, okay? There is guaranteed to be an absolute minimum or absolute maximum for and absolute maximum for f on a closed interval AB, as long as f is continuous on the closed interval AB. So notice it doesn't have to be differentiable even, okay? Just continuous, And that guarantees you have an absolute maximum and an absolute minimum. Okay. We also then talked about relative extrema. Okay, relative extrema, or also sometimes called a local extrema. Okay, it's kind of like a maximum or minimum for like a neighborhood of points. Okay, hills or peaks in our graph indicate relative maximum. Valleys or troughs indicate a relative minimum. Right, and so then we went through and kind of like determined the location there, and we were able to kind of see that where these relative minimums and maximums occurred, okay, that it looked like the derivative was either going to be 0 or did not exist at those points. And so in fact, we came up with the idea of the critical number, right? Critical numbers are where the function, okay, its derivative, is equal to 0 or undefined. That identifies a critical number, okay? A critical number, right, is kind of like a more general set of numbers, right? And then specifically within that subset, we have the relative minimums and relative maximums. So what I mean by that is, right, you can have a critical number that's not necessarily a relative minimum or relative maximum. But if you have a relative minimum or relative maximum, you can be guaranteed it is a critical number of the function f, right? So if you have a relative minimum or maximum, that means guaranteed the derivative must be either, the derivative of the function must be 0 or undefined at that location, right? But just because you have a critical number doesn't necessarily mean it's a relative minimum or relative maximum. And we'll see about how we can determine whether a critical number is a relative minimum or relative maximum later. Okay. So again, we went through, found some critical values here, set the derivative equal to 0, all that fun stuff. Yep. And there again was what I just kind of said about how relative extrema only occur at critical numbers, but critical numbers are not automatically relative extrema. Okay. And then we talked about finding the absolute extrema. Okay, so we actually do have a tool or a way to find the absolute extrema right now. Okay, can't necessarily find relative extrema just yet. We can see them in a picture, but we can't use calculus yet to do it. We have the tools. I haven't taught it to you yet. With absolute extrema, the idea is the absolute extrema either occur at a critical number or the endpoints of your interval there. Okay, and so again, to find an absolute maximum or an absolute minimum, take the derivative set equal to 0 or undefined, get those critical numbers, and then evaluate the critical numbers, so here in this case 0 and 1, Evaluate those, and then also evaluate the endpoints of your interval, so 7 and 16 are the values there, and just identify where is the highest value. Well, in this case, 16. 216, right, was the absolute max, and where was the absolute minimum value? Well, it's -1, and so it's the point 1, -1. That's your absolute minimum. Okay? So again, that was all on the homework from last night. All right, and we had a nice little summary here of the different things that we talked about at the very end. All right, so moving into what we're going to do today, we're going to be learning 2 new theorems, okay? And so our goal for today is to be able to use and apply Rolle's theorem and the mean value theorem, okay? So 2 more named theorems, so 2 more important ones that you really want to make sure you have down and are able to understand and apply. All right, so to get into things here, I actually have an activity for you all to try, okay? So what I'd like you to do is in a graph, and you can use this space right here if you want to first, okay? Just graph the points 1, 3, and 5, 3, and then draw any random function that starts at 1, 3 and ends at 5, 3, okay? I think, I think you should make sure to draw a continuous function there, okay? I think you should make sure, but I don't think you necessarily have to. Well, I guess you don't have to there, but anyway, you can draw whatever you want. So go ahead and then answer those questions there. Once you've drawn that kind of random function, okay, then answer these 4 kind of bullet points, okay? And for the 5th bullet point, you can kind of use this other space right here if you'd like. Okay, so this, for your first one here, and then you for that 5th bullet point where it asks would it be possible to draw a differentiable graph, so that there isn't a point for which the derivative is 0, and you can go right there too. Okay, so give that a try, see what you're able to come up with, and then we'll kind of come back together, I guess, on that. And draw those graphs, or draw your first graph at least, right? And then kind of answer these questions. You can write it down, write down your answers. So again, once you graphed, is there one point on the graph for which the derivative is 0? Okay? Could there be more than one place where the derivative would be 0? And if so, draw an example of this function. Okay. So you might run out of space there. You might have to or maybe you can use your pencil and erase. Try it. Wasn't the 4th bullet point? So you have some graphs that you've sketched to answer the previous questions. So describe what the continuity of that function would be, or the differentiability. Okay? So, you would look at your graph and determine if there's any places where it wouldn't be differentiable or not continuous or something like that. Now, granted, I did, kind of say it would be a good idea to draw them all continuous here, but you didn't have to, I guess, according to the directions. But it's gonna, yeah, if you don't draw it continuous, it could be really just, I don't know, not super helpful, I think. Okay, so I got some graphs up here for us to look at, consider. All right. Looking at this first one, is there one point on this graph where the derivative is 0? What do we say? No? Okay, why not? What's the problem here? What's the problem? But I mean, like, what's happening here that results in not being ever 0? You know, you have the sudden changes, right? Where it suddenly changes from positive slope to negative slope, and then from negative slope to positive slope, and then back to negative slopes again. Okay? So there's no place where the derivative is 0 here. Here, though, how many places does it look like the derivative would be 0? Probably just one, right? We have like a relative minimum in here somewhere. Okay, it's probably just one. Okay. Could there be more than one? Well, now let's look at this one. Does it look like we could have more than one places where the derivative is 0 here? Yeah. Yeah, right, because we have a relative max here, relative minimum here. So certainly those would be critical points. Derivative would have to be 0 there, right? Okay. And so then here's an example of none, right? Here's a place where none of the, where nowhere on the function would there be a place where the derivative is 0. Okay. Now, the last bullet here then is the question, is it possible to draw a differentiable graph so that there is not a point for which the derivative is 0? Explain your reasoning. So in other words, right, here I was able to draw a graph that was not everywhere differentiable. Okay, I was able to avoid the derivative ever equaling 0 here. Okay, right, I could never get the derivative to be 0 because of the points. But is it possible to draw like a differentiable graph, right, nice smooth curves like this? All right, is it possible to draw a differentiable graph such that there is not anywhere where the derivative would be 0? Again, using the same kind of constraints here where we're trying to connect the 1, 3 to the 5, 3. Is it possible to go, my pen's dying here, I think. Okay, so, R.I.P. my pen. All right, 1, 2, 3, 4, 5. 1, 2, 3. Is it possible to get from this point to this point using a nice smooth curve and avoid having a derivative of 0 at some point there? So what do we think? If I go up, what do I have to do? Go back down, which would then create a relative maximum. If I go down, then what do I have to do? Go back up, which would create a relative minimum, derivative would be 0, right? If I go straight across, it's a horizontal line, and the slope would be 0. Okay, so basically, there is not a way to do this. And this is the fundamental idea of Rolle's theorem. Okay, so we're going to fill that in here right now and identify what Rolle's theorem is. So, what were our stipulations, right? If f, so let f be continuous on the closed interval AB and differentiable on the open interval AB. I forgot the word on here. Okay, so let f be continuous on the closed interval a to b and differentiable on the open interval a to b. Okay, so that's kind of our prerequisites there. a third prerequisite, if f of a equals f of b, which is our case in this scenario, right? F of a, we had a y value 3 here, we had a y value of 3 here. So if f of a is equal to f of b, okay, if the function, if I would add those two endpoints of our interval is the same value, if the same y value there, then there is a point C in that interval AB. Ooh, I hope I wrote that right. Okay. Such that f prime of C has to equal what? 0, right? It's got to equal 0. That's what we were just showing here, right? That if you have a continuous and differentiable function on an interval, okay, if you have a continuous differentiable function on an interval, a to b, in this case it was from 1 to 5, and if f of 1, in this case, if f of a equals f of b, in this case f of 1 was 3, f of 5 was 3, so they were the same value. If their y values are the same in the function, then there's at least one point C in that interval such that f prime of C equals 0, right? And so we saw situations where there was 1 point, there are 2 places, there's an infinite number of places there, okay? So again, you can kind of see it demonstrated here, right? In this scenario right here, right, from the interval from a to b, we have a continuous differentiable function, okay? So f is continuous on AB. F is also differentiable from A to B, and we can see that we have that f prime, oh sorry, I should also say, and f of A equals f of B, right? You can see right here is the y value f of A equal to f of B, right? They have the same height, well, roughly, there's just a sketch there, okay? And so therefore we have a place f prime of C is equal to 0 right there, okay? There's that horizontal tangent that we're guaranteed. Okay. So the Rolle's theorem guarantees the existence, okay, guarantees the existence of a 0 for our derivative, or the existence of a horizontal tangent line for our function, okay? That's the best it can do, though. It doesn't tell us where it is, right? We can figure that out sometimes. But the best we can say is that the derivative must equal 0 at some point. The derivative must equal 0 at some point. All right, whereas over here, right, is our function f continuous on the interval from a to b? Yes, right? It's smooth curve. You can kind of trace it with your pen. There's no jumps, holes, gaps, no vertical asymptotes or anything like that. Is the function f differentiable from a to b? No, right? We have a sudden change from a positive slope to a negative slope right here without like kind of a transition there. Okay, so f is continuous on AB, but f not differentiable on AB. F of A does equal f of B still, right? They still have the same height, but f prime of C never equals 0. Okay, there's no place where that derivative is going to be 0, and it's just because it's not differentiable. Right, in the interval there. All right. Questions on anything regarding Rolle's theorem, or at least the idea there? We're going to need some practice with it here. Okay. So, example 1, determine whether the function f of x equals sine of x over the interval from pi over 6 to 5 pi over 6 satisfies the conditions of Rolle's theorem. If it does, then find the guaranteed points. Okay? So, what are the 3 conditions for Rolle's theorem? Condition number 1, the function must be continuous. Condition number 2, the function must be differentiable. And condition number 3, f of A must equal f of B. Okay? So, condition 1 is f continuous. Oh, sorry, I should say f continuous on the interval, right? We don't necessarily, so that's like a little thing we want to be careful about, right? Sometimes we have functions that aren't continuous, but if the point where it's not continuous is not in the interval, then we can still consider it continuous. It only needs to be continuous on the interval, not for the whole function. Just continuous on the interval. So is f continuous on this interval? Yeah, right, it's sine. Okay? Is f differentiable on pi over 6, comma 5 pi over 6? The open interval there. It is, right? Because what's the derivative of sine? Cosine. And does cosine have any problems with numbers between pi over 6 and 5 pi over 6? No. So the derivative of sine, cosine, has no problem. So therefore, sine is differentiable at pi over 6 and 5 pi over 6. So yes. Okay. Does f of pi over 6 equal f of 5 pi over 6? Okay. Yeah, f of pi over 6, so it's sine of pi over 6, 1/2. Sine of 5 pi over 6, also 1/2. So check, yes. Okay. So with those three conditions met, Rolle's theorem applies. Okay. So there is a C in the interval pi over 6, comma 5 pi over 6, such that f prime of C equals 0. Okay, and again, I'm really spelling it out here, just because it's helpful. We're just learning this, right? We have to meet these three conditions. We can then say that Rolle's theorem applies. Therefore, there must be some C value between that pi over 6 and 5 pi over 6 such that f prime of C equals 0. Now we're supposed to find that guaranteed point. So how should we go about finding what that point is? We could graph it. We want to know when the derivative is 0. So what should we do? Set the derivative set equal to find the derivative set equal to 0. Right? That's all we got to do. So derivative of sine, cosine. So we'll just take cosine of x, set it equal to 0. Okay? Cosine of x, set equal to 0. And so that would mean that x then, when does cosine of x equal 0? Pi over 2. Why didn't you say 3 pi over 2? It's also in cosine 0. 3 pi over 2 is not in the interval. So I'm going to write it here. Okay, I'm going to put it there, right? And of course, you can do comma, an infinite number of other ones. But I'm going to cross it out because it's not in the interval. Okay, so there is our point. Okay, and of course, if we graph this, we can see. I'm going to use a pencil here to graph this. Let's see. I guess I'll go from like 0 all the way out to 2 pi here. Okay. So 1, -1. Okay, so sine from 0 to 2 pi looks like this, but obviously we're not interested in that. We went from pi over 6 to 5 pi over 6. So we'll say pi over 6 is, I don't know, like approximately, actually it should be like at 1/2. That's actually not that hard to identify. Something like right here, we'll say. So I'll erase away that piece. And then 5 pi over 6 will be when we're at 1/2 over here. So, oops, I really messed that graph up, didn't I? I was supposed to go through pi. Goodness gracious, Mr. Wood. Sorry about that. Sorry. Should have been like this. So yeah, actually should have gone down there, and then back up to there. So I messed that up. But anyway, so now we're back up to the 1/2 though, so it'll be like, I don't know, like roughly right there, we'll say. Okay. My apologies there, guys. Focused on trying to draw the graph well, and don't do it. Okay, so what we end up with is something that looks like this. This little piece right here. Okay? They both have that y value of 1/2. They both have that y value of 1/2. Okay? So f of a equals f of b. Right? And we can see where that guaranteed 0 is right here. Okay? M equals 0 right there. So there's that, or f prime of c. Okay? So the c value, there's our c. And I'll say f prime of c equals 0 right there. Okay. Okay. So there it is kind of visually, right? There it is visually. We have a nice continuous and differentiable curve from that pi over 6 to 5 pi over 6. And then we have that c value there guaranteed between the pi over 6 and 5 pi over 6 where the derivative will be 0. Okay. So there it is. All right. So let's try another one here. Okay. So example 2, find the two zeros of the function and determine whether Rolle's theorem can be applied on the interval of the zeros. If Rolle's theorem can be applied, find the values of c such that f prime of c equals 0. Okay. So now we're not given an interval. Okay, we're not given an interval here. We're told to come up with an interval and let the interval be between the two zeros, okay, of these particular functions. Okay, it's helpful to use the zeros because, well, if we're finding the zeros, that means they're already guaranteed. We have the same function value, right? They'll both be 0, so they'll both be on the x-axis. Okay, so that's why we kind of do that. So we'll take our derivative, or sorry, not our derivative, our function here, set it equal to 0. Okay, and so you get x minus 3 equals 0 and x plus 1 quantity squared equals 0. And so you get x is 3 and x equals negative 1. Okay, when you square root the 0, it's still 0. Subtract 1, you get x equals negative 1. So our interval is from negative 1 to 3. Whoops, I don't know why there you go. Okay, from negative 1 to 3. Is f continuous on negative 1 to 3? Yes, right? It's just going to be a polynomial function. No problems there. So yes. Is f differentiable on the open interval negative 1 to 3? It's like, yeah, yes with the question mark? Okay, so let's see. All right, we can take the derivative of this. So here again, right, is what I was kind of talking about yesterday, where now it's just kind of expected we can take the derivative of things, right? But we have to understand that, you know, all of the potential rules could apply here. So specifically when I go to take the derivative of this function, what rule are we going to use? Product rule and the chain rule in essence, although really the chain rule won't be too bad there, okay? We could, if you wanted to, you could multiply this out first. So you could like square x plus 1, quantity squared, you do x plus 1 times x plus 1, and then multiply by x minus 3, and then take the derivative. That's up to you, whether you want to or not. I'm going to go ahead and just take the derivative as it's written. So let's just examine the derivative of this to make sure we can convince ourselves it's differentiable from negative 1 to 3. All right, so it'll be the second times the derivative of the first. The derivative of x minus 3 is 1, that's nice, plus the first, x minus 3, times the derivative of the second. The derivative of something squared, 2 times that something to the first, times the derivative of what's inside. But the derivative of x plus 1 is 1, right? 1 plus 0, so just 1. Okay? Looking at our function right here, or looking at the derivative, I should say, does it look like we're going to have any issues with plugging in values between negative 1 and 3? No, right? So it's going to be some polynomial here. And so we're good. We can say yes. Okay. Does f of 3 equal f of negative 1? The better, right? Because they're both zeros. So that's why we found them that way in the first place. So yes, that's how we found them. We purposely, found the zeros, so they're both going to have a y value of 0. So yes, they better. Okay. So now Rolle's theorem can be applied. Okay, I'm not going to write this one out this time. We can apply it, right? We met the conditions. So we want to find the values of c such that f prime of c equals 0. So we're going to set our derivative then equal to 0 here. I'll rewrite it like this. Okay, we'll set our derivative equal to 0. And you have some options at this point about how to solve, right? So we've done the calculus part. This is now all algebra, right? This is no longer calculus, it's all algebra. But I'm going to help you with the algebra part too. Okay? Option 1, we could multiply this out and combine like terms, factor and solve and all that stuff. Option 2, factor out x plus 1. There's a GCF here. X plus 1. Factoring out an x plus 1 leaves behind an x plus 1 because it was x plus 1 squared. Plus, and then the x plus 1's gone from here. It's just 2 times x minus 3. And if we simplify what's in those square brackets there, we'll have 2x plus an x, so that's going to be 3x. A plus 1, but a minus 6, so minus 5. Okay, so again, all I do is just combine like terms in the square bracket here. X plus the 2x here, because the 2 is going to distribute. So 2x plus x is 3x. 1 plus a negative 6 is negative 5. Now, I don't know about you. I find this preferable to multiplying that out and then combining like terms. Okay, that's just me though. All right, so we can set each one equal to 0. And so we get x equals negative 1 and x equals 5 thirds. Okay. And so then both of these places are where the derivative would be 0. Okay, both these places where the derivative would be 0. Questions on any of that? Okay, so why don't you guys go ahead and examine letter B here. I know I kind of started writing into it, so maybe I'll kind of... So see if Rolle's theorem applies. Okay, actually, sorry, you have to find the zeros first. You have to find the zeros first. My apologies. So find the zeros. Okay, there's going to be 2. Find the zeros. See if Rolle's theorem applies on that interval. And then if Rolle's theorem applies, find when the derivative will be 0. Find those guaranteed points where the derivative is 0. Okay. Yeah, the rewriting like that is a good idea. So where did the cube go is my question to you. You had it.
Can I take like square off the x and then just make it 1 square root?
No, because this is x being squared, this is x being raised to the 1/3. So you want to get rid of 1 at a time. Okay, so this is the same thing as this, right? You're okay with that, right?
Yeah.
Okay, so what's the first thing we should do to kind of peel off this and get to the xy side? Cube both sides first, and then right? So cube and square root. Since you're square root in the cube settings, you're going to put plus or minus at the end.
Okay. So
that's not wrong what you have there. No. Oh, actually, sorry, it's reversed. So that, the x is cube root of x squared, it's cube root of x 20 squared, and then solve, solve it from there. Yes, oftentimes it is the algebra. Good. Yes.
Square root.
So far, so good. So you start on this part, trying to figure out whether it's differentiable or not. So looking at your derivative, is there any x value that'd be a problem? 2/3. What would it be? Is that integral? Cube root of yeah, and therefore it's not good. Yes. You took the derivative here, which you could rewrite as 2 over 3x to the 1/3, right? That's x to the 1, negative 1/3 times the denominator. X to the 1/3 times the denominator. Yep, like that. Is there any problem x values?
Do you go see the Medea movie?
What's the problem x values here?
Medea? I haven't. You ever heard of
If
Medea?
x is 8, there'd be a problem.
I don't actually.
So if you have an x in your denominator,
I don't think we'll look at it.
therefore not differentiable at 0.
Sorry.
Over at
So is the function differentiable?
No, it's definitely no. No, it's definitely no. Yeah, just thought I'd let you know.
Oh, okay.
Reasonable space. Wait, what's up? Reasonable space.
Oh.
Me and all my friends. Medea?
You're done.
So I have a question.
Okay.
Yeah. I know that if I plug in 0
I
here,
think.
Correct. So therefore the derivative will have a problem. It will be not differentiable.
and that's in the interval.
Yeah. In the interval, so you're done.
So what? So wait, what does that mean again?
Roll does not apply. Okay. All right.
You kind of stopped.
I did on purpose. So is the function continuous on the, so first of all, -8 and +8, those are two zeros of the function, right? So when the function is 0 there, when you have x to the 2/3, remember that is the same thing as x squared, the cube root of x squared equals 4. So then to simplify this, you would cube both sides, you get x squared equals 64, square root both sides, you get x equals plus or minus 8. Okay, right? That's like the worked out problem there, all right? So is f continuous from -8 to 8? Yeah, no problem, right? We can plug in -8 to 8 there, no problem. Is f differentiable from -8 to 8? No, it is not, because f prime of x is equal to 2/3 x to the -1/3. That negative exponent means the x would move into the denominator, which is no bueno if x is 0, right? If x is 0, we have an undefined derivative, which means the original function is not differentiable there. So is f differentiable from -8 to 8? No. Rolle's theorem does not apply. We don't even have to check to see that f of a equals f of b. I mean, we know it is because they're both zeros, but Rolle's theorem does not apply. Could the derivative still be 0 at some point? Yes, could. Right? Rolle's theorem is not, just because Rolle's theorem fails doesn't mean the derivative could still be 0. We just can't guarantee that the derivative is 0. Okay? That's all that an existence theorem can help us with. We can't guarantee it does equal 0. So question?
What would be an example of that?
I would have to take a look at that. I don't have one off the top of my head because that is like a little very specific case, I guess. So, I'll look that up though, and I'll get back to you on that. So, Mean value theorem. Okay, this one we're not going to do an exploration for. We're just going to like jump into it. So if f is continuous on the closed interval ab and differentiable on the open interval ab, then. So if we go back to Rolle's theorem said let f be continuous on ab. So that was like condition number 1. Condition number 2, differentiable on ab. If f of a equals a f of b, that's condition number 3, then. Okay, so we had to do 1, 2, 3. So we had to show 1, 2, 3 things here for Rolle's theorem. Then we could draw our conclusion. When we go to the mean value theorem, there's only 2 conditions we have to meet. If f is continuous on the closed interval ab, condition 1, and is differentiable on the open interval ab, condition 2, then we can now conclude something. Okay, so only 2 conditions to be met there. Then there exists, so the mean value theorem again is an existence theorem. It does not say where the thing occurs, where this thing that we're going to talk about occurs. It is only the existence. Okay. Then there exists a number or multiple c in AB, okay, very similar to Rolle's theorem, such that f prime of c is equal to f of b minus f of a over b minus a. F of b minus f of a over b minus a. That's the slope formula, right? What do we use the slope formula to calculate in calculus? Not the derivative. Well, we use it with the limit to do the derivative, but it's the average rate of change. So, in other words, if f is continuous and differentiable, right, like we said here, then there is some or many numbers c in AB such that what's the derivative known as? Instantaneous rate of change is equal to the average rate of change. Okay, on that interval. Okay, so again, here's just the stuff that I've been mentioning all throughout this. Extreme value theorem, Rolle's, and mean value theorem are existence theorems. This means that there is guaranteed to exist at least one point where the conclusion is met, but you may not know where. Okay, you may not know where. So that's key. So this little diagram here is going to help us kind of illustrate this point. So let's say we've got a function here. Does it look continuous?
Yeah.
Does it look differentiable? It does, okay? So we'll consider it from a to b here. So I'll draw a little a b right there. And we've got f of a up here. And then f of b is like right there, we'll say. So notice here we don't have to worry about f of a equaling f of b. Not necessary for this one. Just is it continuous and differentiable on the interval? Yes. Okay. To illustrate the average rate of change, I'm going to draw the secant line, the slope of the secant line, right? That's the average rate of change. So I'm going to actually draw a line connecting these 2 dots. Okay? So I'm going to do my best here to connect them. Okay, not bad, not bad. All right. So there's our secant line. Okay, this is the m is equal to the slope there is the average rate of change, which is f of b minus f of a over b minus a. Okay. And so what we want to look for, okay, with this diagram is where the derivative or where the instantaneous rate of change or where the slope of the tangent line would have that same exact slope. So if we kind of consider like this pencil here to be the slope of that secant line, we can kind of like keep our pencil parallel to that secant slope and see that, oh yeah, it looks like right about, like here on our graph, we'll have a tangent slope that's equivalent to that average rate of change there. All right? So maybe like right, I don't know, here I'll say. Okay, we'll have that parallel. Okay, and there's like the c value, and this would be then f prime of c equal to the f of b minus f of a over b minus a. Okay. Is there anywhere else where it looks like the derivative might be parallel to that average rate of change? Well, I'd say if we go down, okay, like roughly right there, okay, same situation. So there's actually two c values here. Okay. So there's actually two places where the derivative would be equal to the average rate of change. Okay. So there it is visually, but now let's kind of like calculate it out and stuff like that. So let's go to example 3. So given f of x equals 5 minus 4 over x, find all values of c in the open interval 1 to 4 such that f prime of c is equal to f of b minus f of a over b minus a if they exist. Okay? So, in other words, does the mean value theorem apply here? Well, is this function continuous? Not at 0, but is 0, like, very good point, is 0 in our interval? No. So is this function continuous on the interval? Yes. Okay, so remember, again, we're not worried about being continuous everywhere, continuous on an interval here, and then differentiable on an interval. So it's continuous on the interval. Let's also check our derivative here. So our derivative, f prime of x, well, let's see here. I'm going to rewrite f of x first before I do that. So f of x is really 5 minus 4 times x to the negative 1. Okay, right? And so then f prime of x would be, well, the derivative of 5 is 0. The derivative of negative 4x to the negative 1, positive 4x to the negative 2. Okay, or in other words, 4 over x squared. Is our derivative going to have any problems on this interval from 1 to 4? No. Again, if 0 were in the interval, it would not be differentiable at 0 either, but the function would not be differentiable at 0. But since we're just an interval from 1 to 4, we're good to go. Okay? So f is continuous. Oh, I'm going to write it out. On 1, 4, and differentiable. Mean value theorem applies. Okay, mean value theorem applies. So we want to locate the point C where the derivative is equal to the average rate of change. So let's first of all find that average rate of change. So we'll do f of 4 minus f of 1 over 4 minus 1. Okay, so you can plug 4 in if we want to. 4 over 4 is 1. 5 minus 1 is 4. We can plug 1 if we want to. 4 over 1 is 4. 5 minus 4 is 1 over 4 minus 1. So this is going to equal just 1 here. Alternatively, you could have looked at the graph and found the average rate of change by counting the slope. Rise, 1, 2, 3. Run, 1, 2, 3. 3 over 3 is 1 as well. You also could have just counted it. Okay, so your choice. Your choice. All right, then we said the derivative equal to that. So 4 over x squared equals 1. Okay. We set our derivative equal to the 1. And we're going to find this value that's guaranteed where our derivative is equal to the average rate of change. Or the instantaneous rate of change equals the average rate of change. So we'll cross multiply here. We get 4 equals x squared. And so we get x equals plus or minus 2. And so our answer then, where the derivative must equal the average rate of change, is positive 2 or negative 2. No, but that's what I got here. Oh, negative 2 is not in the interval. Ah. So just 2. Okay, only 2. Questions on any of that? Okay. Example 4 here. Given that f of x equals 4x plus 6x to the 2/3, find all values of c, if any, in the open interval negative 1 to 1, in which the average rate of change is equal to the instantaneous rate of change. If we're trying to locate where the average rate of change is equal to the instantaneous rate of change, what are we applying here? What theorem? This is mean value theorem. Okay, so this is like a subtle way or a discrete way of really just asking us to use the mean value theorem here. Okay, so go ahead, do it. Give it a shot. Okay, I think you guys have all the information. You're supposed to check the interval -1 to 1 first, then check the interval from 1 to 8. Okay, so that's going to change your calculations, right? Because -1 to 1, that average rate of change potentially is different, most likely is different than the average rate of change from 1 to 8. But of course, check to make sure you're continuous on your interval and check to make sure you're differentiable on your interval first, right? You got to check to make sure those things apply. All right, so go ahead and give that a try for both intervals there. Yes. What do you mean by work out cleanly?
Does it come out to a nice looking number?
Probably not.
It's, it doesn't never get.
But I got 36 on my, so that's good. I didn't even know.
That's a value, that's a theorem. Not Rolle.
Okay. In the interest of time here, we'll keep going. All right. So, I just did that there. Interesting. All right. Anyway, so what we've got here is zoom in some. All right. So for the first interval from -1 to 1, the average rate of change. Okay. We can find that, right? We could also take the derivative and set it equal to. And set it equal to that and solve, but the problem is the mean value theorem here doesn't apply. All right, does not apply. So f is not differentiable at 0. Okay, and therefore our derivative, right? And so in other words, our derivative would be undefined when x is 0, and so the mean value theorem does not apply. Okay, the function is continuous on the interval from -1 to 1, but it's not differentiable, and so mean value theorem doesn't apply here. Okay, does not apply. Could we still find the place where the average rate of change is equal to the instantaneous rate of change? Potentially here. Okay, potentially. But the mean value theorem doesn't apply. Okay. For the second piece, all right, I ended up with 2,744 over 729 for the answer. It does work. Okay. Or in other words, 14/9 to the third. 14/9 to the third there. Okay. That value. Yeah, absolutely. Yes. Because again, arithmetic, right? Simplification. That's all you have to do. Yep. Questions on any of that? All right, I do want to hit this last one here because it is an actual calculus free response question. Okay, so this is from the 1999 AP free response. Okay, so it's older than some of you in here, many of you in here, all of this. Anyway, I don't have to worry about that. It's younger than me though. So the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function. Oh, I was in 9th grade. The rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. Yes. So the table shows the rate as measured every 3 hours for a 24-hour period. So this is a table of the rates, okay, hours, and then the rate of change there in gallons per hour. What is the minimum number of times, t, for 0 less than t less than 24, in which the flow rate is 11 gallons per hour? Justify your answer. So looking at our table here, what would be the minimum number of times for 0 less than t less than 24 in which the flow rate is 11 gallons per hour? So, ideas here. What's the minimum number of times? Like we can guarantee at least this number of times. What's the minimum number of times that the flow rate is going to be exactly 11 gallons per hour? What do we say? So, Nick?
Twice.
Twice. How did you come up with 2?
Because in between 6 and 9 and 15 and 18, it's below 11 before and above 11 after.
Right. To get from 10.8 to 11.2, and to get from 11.3 down to 10.7, what number do we have to cross through? 11, right? Now, notice we said what is the minimum number of times. We have no idea what's actually going on between these numbers. So for example, from 9.6 to 10.4, could we potentially have gone through 11? Absolutely. We could have, gone way up to like 12 or 15 and then back down. But by the time we checked it again 3 hours later, it was at 10.4. Okay? So don't assume it is exactly 11, but by the information we're given, we can guarantee at least twice it happens. Okay? What theorem we want to use here to justify that? Intermediate value theorem, right? So remember that from way back, right? Okay, we talked before even talking about the derivative, we talked about the intermediate value theorem. Okay, so the minimum number of times. Okay, so we can say like 2 times here. Okay? And our justification, I'm going to run out of time here, but our justification is going to be something along the lines of we have to establish that R is continuous, because in order for the intermediate value theorem to apply, we have to establish that R is continuous. Okay? So R is continuous for 0 less than t less than 24 because R is differentiable. Okay? So nowhere in the problem are we told that R is continuous. Nowhere are we told that R is continuous, but we are told that R is differentiable. And since differentiability implies continuity, we can assume R is also continuous. So R is continuous for 0 less than t less than 24 because R is differentiable for 0 less than t less than 24. Okay? And so then, and again, I don't really have like necessarily an elegant way to say this, so I'll just try and just get the information across here. I'll say, you know, since R of, let's see, we'll say R of 6 is less than 11, which is less than R of 9, and we'll do the other one here, R of 15, I guess I'll go the other direction. This might be a little bit weird, but I think you can write it this way. R of 18. Okay, so R of 15 is greater than 11, which is greater than R of 18. Then the intermediate value theorem guarantees, I forgot my N for guarantees. R is 11 in those two intervals. Something like that. Okay? And we'll stop there and we'll finish up B and C tomorrow. Okay? Your homework is on the Google Classroom. Okay? Your homework is on the Google Classroom. If you want to try B and C, feel free. Okay? I mean, you have the skills to do it, so maybe try B and C, but if you don't, we'll finish it up tomorrow and then we'll get into the next section too, 4.3. Okay? Yes.
Rolle says that the water flows out of the pipe, but then C has a negative value, so are we allowed to assume the water cannot flow back into the pipe?
I think so, yes. Yeah, the flow out is, I guess, considered a positive value, right? And so then the flow in would be considered negative. Yeah. So, set requests for today. Emily, whoops. Okay. Morgan, Emma, Chase. All right, Morgan, Emma, I got you. Oh, sorry, got you. Ariana got you, and then Cece got you too. Sign you in, Julia up. Okay. Gotcha. Yep.
Thank you.
Cassie, Julia.
Well, I can write my name.
Okay. And then.
And I need to say
Okay.